Let's take a look at homework 14.2. This problem is liquid octane burned in a combustor with air and including some excess air. I have an example problem posted here so you can follow along with that as well. But let's just look through the problem. So we've got air as 21% oxygen, 79% nitrogen. We're given a specified amount of fuel. The temperature of the fuel and the air are different, 100 degrees C, 60 degrees C. The exhaust temperature coming out of the combustor is 1226.85 degrees C, and we've got 25% excess air. If we look at this example problem for liquid octane, it has also a specified amount of fuel, but it's 1 kilomole. So here we're doing an energy balance for 1 kilomole of fuel. And if we do that, we can solve for the balance the carbon atoms on each side, the hydrogen atoms, the oxygen atoms, nitrogen atoms. When we do that, we can find these coefficients, beta, gamma, delta, and epsilon. For 1 kilomole of fuel, we find out with 25% excess air that alpha is 74.4, and then beta is 8, gamma is 9, delta is 58.74, and epsilon is 3.125. In general, for any hydrocarbon fuel where the carbon atoms are X and we have the hydrogen atoms are Y for each molecule, we can write that beta is X, gamma is Y over 2, epsilon 2 times beta plus gamma times lambda, which is our excess air. In this case, we don't have we have 25% excess air here, so lambda is 0.25 divided by 2, and then we can find alpha from our epsilon, or you can find that directly if you want. Then delta is 0.79 alpha. So this is in a general sense for any hydrocarbon fuel. So let's go back to the problem. This one. And the first thing we want is the air-fuel ratio. So we just found that to be 74.405. So this is very similar to the homework 14.1. The amount of fuel burned, this is going to be 166.67, which is the mass. Let's write that just as the mass of the fuel divided by the molar mass of the fuel, which will be then the number of moles divided by, if we look up the molar mass of octane, you can find that in table leave A1 of your book. And for octane, it's 114.22. So we do that and we'll get 1.4592 kilomoles of fuel. Then the amount of CO2 produced, we found from our balanced equation that that's 8 kilomoles per mole of fuel. So this would equal then 8 times 1.4592, which will give us 11.67. And just to be clear, the website doesn't allow you to type in formulas on these. It's expecting a numerical answer. Then same thing for the H2O. It's going to be 9 times the 1.4592. So on for each of the components. So if we had 1 mole of fuel, then it would be 8 times 1, 9 times 1. But in this case, we have 1.459 kilomoles of fuel. Then finally, when we get to the enthalpies of CO2, we need to find the enthalpy of CO2 at 1226.85 degrees, and then we would multiply that times the moles of CO2 that we have, or times 8 times 1.4592. Let's go look at how we would find that. For 1226.85, the degrees C, that's going to be exactly 1400, let's see, 1500 rather, Kelvin. And if I go to my website, I mean, I can use the tables, but let's see if I can find that here. Let's make a new page. Actually, I think I have it on my website, the Blackboard site. If I go to semester project and enthalpy for products of combustion, I'm going to download this, open it, and I've got for CO2 at first column here is temperature, and let me just lock this. So when I scroll down, I can see what column I'm looking at, and at 1500 degrees I have 72,246. So trying to get down on top again. Sorry, it's 71,078. So equals 71,078. That is at 1500 degrees, then minus at 298, which is 9364. And then I also need to add in the enthalpy of formation. And for CO2, it's negative 393,520. And you'll find that either in table A24 or at the top of the column, right up here at the top of the column on table A23 in your text, you'll find that enthalpy of formation. That enthalpy of formation is based on, let's just press enter and put that here. So that HF0 is negative 393,520. That's a kilojoule per kilomole, and that is at reference of 298. So that is why when we write this out, we're comparing our temperature to the reference temperature. So we take our enthalpy at 1222 C or 1500 K minus the 298 K, because that's the temperature of the reference, not the temperature of the inlet air, the inlet fuel, the surroundings. So this second temperature is always going to be what this enthalpy of formation was at. So that is our enthalpy lowercase h per unit mole. And to get a capital H, we take this lowercase h times the number of moles. So we have the number of moles in this problem was, if I look at my answer sheet, or we can go back to the problem here. If I can find the page again. We had for CO2 11.6736. Times this enthalpy. And we'll get a large number here. This is 3,873,000, and that will be the answer for G. Don't know if it will let me copy and paste the number, but we can try. And submit that. It doesn't like these answers, but so we do that for H2O, N2, O2, continue on for all the products. Of course, each time calculating the enthalpies from the charts. Now, if you wanted to automate this process, what I've done here is at the top of the page, I've made a graph, and I've made a curve fit for the data. So this data that I'm looking at is temperature and the enthalpy of CO2. I could do the same thing for the other gases. So if I just take this and stretch it over here, I'll find out that a sixth order polynomial gives me a very good fit. It's hard to even tell the difference between the curve fit and the function here. Maybe if I zoom in a bit, you still can't really see it. Very, very small error there. I can move it over and look at the function for O2 and the function for N2. So you can do that. You can take those functions, do those curve fits. Let me just show you how I did that. So we put this one back and just make a new one. So I'm going to make a new graph. Let me push this one off to the side. So I'm going to insert graph. Actually, an easier way to do that is just to highlight some of the graph, insert a graph with that data, and then just grab the data you want. So I'm going to take this and put it to my second column. And then, of course, works best if you use all the data. So I'll select all the data, and then my graph's up here. So I'm plotting the enthalpy of H2O as a function of temperature. And if I right click on that and add a trend line, choose what kind of trend line. I'm going to choose a sixth order polynomial, which is high as you can go with Excel. I'm also going to display the equation on the chart. And then unfortunately the number of digits will not give you the most accurate value, so I'm going to right click and format the label, and let's see, somewhere here it lets me choose it is scientific, and I can choose maybe 6 digits and make a little space. And now I've got my function. If you want to plot that just to see that you have it right and it looks correct, you can do Control C and Control V. You can paste that, and then of course this power you have to type in a little differently. So I'm going to take the, not sure what cell I'm working on here. Let's see. All right, let's put it here. So paste that and put it equals, and raise this to power. And the cell I'm looking for is this one. Doesn't like that. Let's see. Equals, let's just type it in, B4. And then I'm going to just copy that, paste that each time for my power. Of course, last time's the power 1, so I don't need that. Alright, so there is a fit of this value, and then I can just copy that down. And each time it's using this temperature in my sixth order polynomial. I can do the same thing for O2 and N2. And then if I wanted to put that in my program, so now I have for H2O this function, or better yet, take this again. Actually, this is probably okay. We'll still have to modify it a little bit. All right, now I'm going to, I believe I sent you a program called Calculator, Combustion Calculator. And actually, I want to open that with an editor. You can open it in Notepad if you want. So I have this combustion calculator, and I'm trying to put in an equation for H2O. So now I've got my equation. The only problem is this equation is just the enthalpy as a function of temperature. And here it's as a function of log of temperature. So I'm going to change that. But so right now B4 is my temperature. So I'm going to just replace that with T. Actually, let me put it as TE, the exit temperature. And this programming language likes double star for power rather than caret. Caret has a different function. And then the enthalpy, I need, this is my enthalpy is a function of temperature, so I also want to know what the enthalpy of formation is, add that in, and then minus the temperature that that function gives us at the temperature that the enthalpy of formation was calculated at. So for H2O, the enthalpy of formation is negative 241,820. And plus minus, so I'll leave that as a minus, so I can do plus in parentheses if I want, just to keep that function straight, and then minus the value at 298 degrees. So if I go back to my equation here, and for my H2O, 298, I can either use the fit or this value 9904. I'm just going to use this value here, 98.431. That way at the temperature of 298, I'll get exactly that same value, and I'll just get the enthalpy of formation. So that's how I did this other one. The only difference is this one I actually used the log of a temperature. So I'm going to take that line out for now. And I can put in my equation for CO2. And that equation I have here. And fitting it here. And for the CO2, I have negative 393,520 plus, put my function in, minus at 298. Let's use the value from the function. copy this value. Let's see if it will. Sure enough, and actually I get more digits, so let me do that on the other one as well. For my H2O. Alright, and let's make sure that ends in a semicolon, and then I need to place this with TE. Actually, should have done that all at once, but can still go back and fix it. Then I simply do that for the other gases. Here I have the total moles, so I need to multiply by something, which will be my, for the H2O is the gamma, so the gamma times the moles of fuel, so gamma times fuel times the enthalpy per mole of fuel, and then times gamma. So this is the total moles of fuel, or total moles of H2O, times the enthalpy per mole of H2O. And then these equations are all incorrect, so you need to fix that. Do the same for N2, the equation, the number of moles of N2, the O2, the equation for it, and then the enthalpy of formation for those is 0, both of those. So when you do that, also this last equation here is incorrect. You'll notice it's missing a fuel, or missing one of the products of combustion. This section's fine, it'll print those things out. Needs the oxygen equations for oxygen and nitrogen for the at the temperature of T air. So if you redo that, you'll just do that as a function of T air rather than the log. So we use that for T air, so we don't really need that equation there. T air is defined. So you put those functions in. This time, instead of a function of TE, is a function of T air. So, you know, something, some constant, rho 0, the enthalpy of formation, plus your sixth order polynomial, you know, whatever it is. And so on. And then again minus the value of oxygen at 298, which in this case will be 8642. And of course, you'll change that to whatever those appropriate maybe minus some number, you know, and so on. T to the 5th. Look something like that. Sixth order polynomial. Of course, you'll do it from just repeating this. So taking your plot here, do it for oxygen, you'll have a function like this. And to do it for nitrogen, just get the coefficients from here. It's really pretty easy to do. Get a nice fitting function. Let me show you what you can do if you finish that. So once I enter those equations, it's a function of TE for all the products, as a function of T for all my reactants. And then the fuel, I've got that equation in there for you. Put in the enthalpy of formation and a CP as you run the program, and it'll calculate all the enthalpies of the reactants and the products. And one last section you need to fix is the equations here. Those you already have for general hydrocarbon fuel CXHY from the sheet. So just type in those formulas. Of course, use the terms that are defined. So I have X and Y defined, lambda defined, and then this equation can be after this because now alpha is defined. So you can use the things that you define in the lines after you define them. Just make sure every term ends with a semicolon. And when you do that, just show you the usefulness of it. Let me open that in. I like it better in Chrome. There we go. So let's try this problem. So this is homework 14.2, and I type 8 carbon atoms, 18 hydrogen atoms, 25% excess air. The exit temperature is 1226.85. The air temperature is 60 degrees C. Fuel temperature is 100. The enthalpy of formation for the fuel for octane, it's liquid octane. If you go to table 8.5, you can find liquid octane, and it is negative 249,910. Specific heat's given in the problem as 2.28. It's a liquid, and the amount of fuel is given as 166.67 divided by the molecular weight, or molar mass, 114.22. And if you type all that in and click calculate, it should work. Let's see. This is why I like this program. So, okay, this is the combustion calculator. The combustion calculator isn't finished, so let's try. One that is. I believe it's this one. And I want it to open in Chrome. While I'm here anyway, if I right click and choose inspect, it'll show me that I have an error, something I typed wrong, and I'm missing a semicolon somewhere on line 79. So if I go here and something it doesn't like here. It's probably because of what I've typed up here. So maybe without an end parenthesis. So let me go back to mine. Try 18, 1.25, 12, 26.85. Air temperature 60, fuel temperature 100. Negative 249,910. This one gives me everything I need. So you have the template there. Just need to put in the equations for the enthalpies, put in the equations for balancing the moles of each component, and you'll have a problem. You'll have a program that can solve every problem. If we go back to problem 14.1, problem 14.1 asked for the balanced equation for dodecane. Believe we really need anything else here. Actually, I can just rerun it. And this will give me all the components. Believe it was no excess air. The only thing given was the amount of fuel, so this was 100 kilograms. And it was dodecane, which has a molecular weight of 170.328. So that is going to change my coefficients because I don't have a mole of fuel. So I have 0.587 moles of fuel. So that's homework 14.1. Homework 14.3 I could also do with my finished program. And grab that one. I think I have it here. And this is methane. So since C doesn't have a subscript, it's by default to 1. 1 carbon atom, 4 hydrogen atoms. This is 100 kilograms of fuel, but 16.04 is the molar mass. And let's see, what else do we need? 25% excess air. And we don't really need anything else. We do need a temperature, which is unknown. So right now, if I run this, it'll give me a balanced equation. If I put in an exit temperature, let's say 1500 degrees, it also needs enthalpy of formation, and enthalpy of formation for methane is negative 74,850. And since the fuel, the air temperature and the fuel temperature are 25 degrees C or 298 K, I don't need to enter them. It accepts those as the default. So here I have negative 1.6 million, so a lot of heat transfer out. So apparently it's not insulated, so I can go a little higher and try and get that Q to come down. A little higher. You see it coming down. Let's try 1800. Still negative. 1900. Still negative. Let's try 2000. Still negative. 2100. Of course, each time we're doing this, you would have to go back to the tables each time and recalculate everything, so that would take you a while. So somewhere between 2000 and 2100. So let's try 2050. That's better. Let's try 2041. Even better. So between 2010 and 2015, so 2014 it's negative, 2015 still negative, so let's go 2016, so it's positive. So it's between 15 and 16. Of course, we can keep going. I believe it's 0.895. Maybe I was wrong. So 2015 is negative. And of course, you could do some calculations, like calculate as a function of the two enthalpies and the two values. So between 0.1 and 0.2. Now you could make a program that would do that for you, that would iterate until it got to 0, but you can quickly find it, especially if I took a little time to just write two values down and do linear interpolation between them. I'd probably converge on it very quickly. But if you did this by hand with the tables, there would be a lot of calculation to try and get to a very accurate answer. So hopefully you see that it's a benefit in writing a program. You can find that program, well, the tables on the website. I think I'll also put this combustion calculator in the project area on the Blackboard website in case you weren't able to find it through the email.